Hello, this is Tony Nichols. I am the co-founder and Chief Technology Officer of Great Ideas. This video is one in a series of videos on enterprise architecture with a focus on data architecture. And we're going to be using some examples from Microsoft.NET Blazor, Azure, and Great Ideas Trellis Spark. And our focus today is on data flows in general. And we'll be doing another couple of presentations where we will look at specifically inbound data flows and outbound data flows. So let's get started. So to understand data flows completely, we need to ask a few basic questions. First of all, why do we need to move data in the first place? And then why should we use a set of data in motion components? So why should we go through the process of making this a generic service rather than just implementing a bunch of point-to-point solutions? Clearly, our focus in this tutorial is going to be around decoupling. So we're going to look at why do we decouple information systems as it relates to data in motion? How do we decouple information systems? And then if decoupling doesn't meet the requirements, what do we do instead? And then finally, as always in this video series, we'll look at how does this impact sustainability of the solutions that we build. So the first question we need to address is why do we need to move data in the first place? And the answer is simple, okay? Not all of the data you need will be in the data at rest, the system record for your record information or files and so on. Some of that system will be in other information systems. So we're going to need to share data with those other information systems. And that sharing may be data coming in, so inbound information from other systems, or outbound communication to other systems. And these are very specific communication flows that we will cover in separate lectures. So we'll have a whole lecture on inbound communications technologies and then a separate lecture on outbound communications technologies. What this tutorial is going to do is focus on the commonality. So one thing that we're doing is sharing data. Now, why are we sharing data in the first place? Well, the obvious answer is we need to be able to optimize an operation, a business task, potentially across different business units that may have different application architectures or different applications. And we may also be interacting with third parties, with customers, with suppliers, with regulators. So essentially to optimize our operation at a business level, we need to be able to share information with other systems that are not part of the scope of our data agnostic services, and therefore we need to transform and transfer information from our own data at rest storage areas into whatever storage is being used in these other applications. And essentially, the point of this is that the exchange of data enables us in some way to generate additional value in our business operations. So looking at it from an internal perspective, I might have a bunch of legacy or custom or proprietary applications that I still need within my organization. I might be dependent, for example, on an old ERP solution, or I might be dependent on an old HR solution, and I need to be able to get information from those old solutions and bring them into my data agnostic services architecture so I can use that data in some way to automate business process or share information or to produce reports. I may also have an issue where I've got a large enterprise and some of my business units are remote. Maybe some of them are in North America and some of them are in Asia and some of them are in Europe. Okay? So I might need to be able to move data between large business units so I can start to produce consolidated reports. The other option, if it's not internal, is therefore it must be external. Okay, so sometimes I'm going to be transferring information to cloud service or SaaS solutions. So for example, I might be using Microsoft Dynamics or Salesforce.com or pick an ERP provider, ServiceNow. And I might need to be able to take information that's being generated from within the scope of my data agnostic services and then be able to transfer it to or from some of these other software as a service type providers or other cloud services. So one example of that, for example, is Azure Data Lake technology with data factories. I might need to be able to take information out of my DaaS solution and take information from half a dozen other applications within the organization, consolidate it all within a data lake to produce some BI reports. So I need to be able to take that data and migrate it somewhere where I can make use of it in a different way. I may also need to share that information, as we talked about earlier, with a third-party application or organization. So maybe I'm getting orders directly from customers via some sort of message queue or service bus, or alternatively, I could be sending out order information to suppliers for fulfillment as well. Obviously, the other option is things like government regulatory, where I need to report on certain types of sale or certain types of fulfillment operation. So anybody who's watched any of the other videos in this series knows that we are big fans of generic components and reuse and not writing code if we don't have to. So one thing that we're going to look at on this slide then is why do we need to build some generic data in motion components? And the bottom line is there are very few different communication technologies when you get down to it. We can send a message to a queue. We can send a message to a service bus queue or a service bus topic. We can create a file that we transfer through FTP as a batch file or so on, or we can be dealing with emails, or we can be dealing with some sort of internal MQ solution. When you get down to it, there are maybe a dozen different ways that fundamentally we can transfer data. Now, if I've got 100 different applications and only a dozen different ways to transfer information, then it makes sense to produce a common generic set of components that I can reuse in many different contexts to transfer information. And a key advantage of being able to do that is that once I have standardized my data in motion components, then I can really get down to focusing on the efficiency and quality of those individual communication mechanisms. And one of the first things that we're going to want to do is look at information security and privacy. So in any communication, whether it's inbound or outbound, we're going to need to make sure that only authenticated and authorized users and applications have access to any data. So if I'm moving data to and from a screen, if I'm moving data between a customer and my internal data store, I'm going to need to know that I've got the right customer and I've authenticated and authorized that customer to make sure that the information is coming from a trusted source. So one of the key elements around communication strategies is that at some point we need to be able to validate both the senders and recipients of data. And then to make sure that once a sender has decided they're going to send us some information and we're going to read it, we're going to want to make sure that we've got some end-to-end data encryption going on, because we don't want somebody in the middle of the transport process to be able to read the information that we're exchanging. So our ideas around these common generic communication components is make sure that we've implemented as many different security checks on that communication as possible. Now, not only do we need to secure our transport method, we also need to have some sort of control and audit mechanism on the data that is being transferred. So this brings in a whole bunch of additional communication standards that we want to have a look at. And these were originally back in 2000 referred to as the WS Star standards. But essentially some of the things that we want to be looking at here is ordered delivery. So if I send messages in a sequence 1, 2, 3, 4, I want to ensure that they arrive at my recipient in order 1, 2, 3, 4. Because if there's some sequence dependency, then if they arrive in 1, 4, 3, 2, then that might break the logic. So one thing that we want to make sure that we have in our communications channels is this idea of ordered delivery. The other thing we want to make sure is that we've got some sort of automated retrial and failure. So if I try and send a message to a recipient and that particular message transmission fails, then it would be nice if I could resend it. Related to automated retrial and failure is the idea of sending only once. So even if I am trying to execute a retry, I don't want to end up with 2 copies of message 3, right? I just want 1 copy of message 3, even if I had to retry it 3 times. As we get into more secure communications, then we also want to make sure that we've got some idea of receipt tracking, so that when I send the message to a recipient, that there is a receipt that the message actually arrived at that recipient, and that I have some sort of non-repudiation, so that the recipient can't deny 3 days later that message 3 ever arrived in the first place. Now, primarily when we're looking at inbound messages, there's another section that we need to consider, okay, is that the integrity of the data at rest service area is also in question. So if I'm ingesting a lot of data from an external third-party source, I don't want to be putting that information right into my data at rest, okay? I want to make sure that I am in some way validating the structure and content of the data as it receives, but before it's being stored in the structure at rest. So one thing that we're going to want to have a look at when we're looking at our inbound technologies is buffering incoming data into some sort of migration table, so we can do some validation on that data before we add it into our record storage. So we're going to be looking at some sort of technologies and solutions around that in our inbound data flows video. So we already talked about coupled and decoupled information system communications. And as you can see, we're highly into the idea of decoupling information systems at Great Ideas and within TrellisSpark. And there's some good reasons for this. Okay, so a highly coupled information system we think are inherently fragile. So essentially you've got application A and it's going to exchange data with application B in real time. Then if B fails, then A is also going to fail. So if I've got some workflow going on in application A, it requires a call to B, B isn't there, or B rejects, then the process in A will also fail. So if we can decouple A and B to minimize that dependency, then it increases the robustness of the system. So if A can send the message to B through some sort of decoupling mechanism, A is happy, the message has been sent. At some point in the future, B can read the message from A, do its processing, and then write the response back to A through another decoupled messaging solution. So one of the things that we don't like when we're building systems is if we highly couple the systems, then it becomes difficult to make changes, and you also increase the dependencies. If one service is down, then it's going to cascade and fail other services. Now, this leads us into the second set of points, right? So we talked about it a little bit here in that if an information system like B is outside our data as a service boundary, it's a risk. right? It doesn't matter whether it's internal or external. So it doesn't matter if B is within your organization or a third party. Okay? If it's failed, so if it's crashed or it's down, or even if it's just running really slowly because there's a lot of performance or there's a distributed denial of service attack running on it at the moment, then it's posing a risk to your operations. So what you need to sort of like really be focused on here is that any sort of communication with any sort of external application, whether it's internal or external to your organization, is a business risk. So minimize those risks is always a good thing to look at. Now, one thing that we talked about is this idea of buffering. So when A wants to send a communication to B, it wants to write the message into a buffer, and then that buffer should be picked up at some later date by B. But that doesn't mean it's a one-step process. So one of the things that we've done with Great Ideas and TrellisSpark is that we want to actually maintain an internal set of buffers before we even attempt to hit the external buffering mechanisms. So what we tend to do is we actually have an internal message buffer within our data at rest service area, because as long as our data at rest service area is available and we're able to run workflow, then we're able to talk to our own internal messaging buffers. Then what we want to be able to do is, let's say we have an outbound communication. So A has written a message into our internal message buffer, and then we would have another TrellisSpark component that would be executing as an independent service that would be reading our internal service buffer and then trying to pass that message on to essentially a third party or an external message buffer. So for example, let's say I'm using an Azure Service Bus as my external message communication mechanism between my data agnostic solution and a third party provider. I would write the communication request into my internal buffer where I am guaranteed that internal buffer is available. I would then have a second decoupling service reading from my internal buffer and making a call to the external Azure Service Bus, which may or may not be there. And then my external third party would be able to connect to the external buffer, the Azure Service Bus in this case, to read the message. So even when you're executing this sort of decoupling technology, don't make the assumption that a third-party system is going to be available. It may even be that you're writing a message to an outbound POP3 client on your own email server, but there's no guarantee that that email server is going to be there and connected. So one thing that we found has always been a wise hop is take it to an internal table within your data at rest storage, because that will always be there. So if I've got an application A, it needs to send a message, it writes to a table, it knows it can always access. And then from there, have a secondary decoupling mechanism, which is taking the data out of that internal table and then passing it on to its next step in the process. So all that being said, how do we best decouple information systems? So essentially, when we're looking at buffered communications channels, then there's a whole different bunch of technologies we might be looking at. It may be events notifications, it might be messages going through a message queue, it might be a service bus for either queues or topics. We might be doing straight file transfer, so a variation of extract, transform, load. That data may be going through an FTP or an SFTP connection. We might be using a shared data store, so we might have cloud storage that we've connected, and we've given SAS tokens to both the sender and recipient, and we put the ETL file into the cloud storage. And then you've got combinations of all of the above. So for example, if I've got to send a really big file, I might put that file into cloud storage and then send an event or a message to the recipient to say, hey, look, there is now a new copy of the file that you want that's in the shared storage. So let's have a look at what that might look like if we were executing this in code. So within the TrellisSpark solution code, we have a library that we presented called REST Logic. And the REST Logic library has a messaging functionality that we built into it. And we built a messaging base class. So this base class essentially is exposing a read method and a send method. So either the data is incoming, so we're going to read it, or it's outgoing, in which case we're going to send it. And we implemented this as an interface. Okay, so essentially what we're saying here is we have a messaging base, which is a messaging interface where either we can send and read messages. And then depending on the particular type of message we're going to send or read, then we will adopt and connect to a particular messaging technology. So let's have a look at how that would work. So let's think about sending messages. What do we think about when we're sending a message? Well, from the interface perspective, I'm going to send a bunch of message information. So if I want to have a look at what message information might look like, I can populate a simple class. So user and session GUID essentially are providing an authentication context for every message that I want to send or read. I might want a particular message GUID, so every message should have a unique identifier. I'm going to use an internal queuing mechanism. So we talked about this idea of having an internal message queue within our data at rest repository, and that will be identified by the name of the message queue. I may or may not have sender and recipient information. So for example, if I'm sending to an email, then a sender and recipient email address is a good idea. But if I'm trying to transfer through, let's say, a service bus topic, then I don't really need a sender. I just need the recipient, which would be the topic address of the service bus. Sometimes I'm going to need a subject, maybe I'll need a format, I may need a body content, and then if something goes wrong during the transfer, I want an error message. So essentially I'm going to use a class that will enable me to send any sort of message information across any of the mechanisms I'm going to use to transfer messages in or out of a data agnostic service. Okay, so how's this going to work? Well, I'm going to want to basically declare myself a container that's essentially going to be running messaging services. And what we're going to be doing is we're going to be taking the data out of our internal message buffer, and we are going to be posting it to external buffering mechanisms. And the way we're going to do that is through this idea of process messages. So let's look at some C# code related to message processing. So what we are going to do is we're going to expose a REST API that will enable us to read or write messages. And so what we have done is we have created ourselves a messages controller, and we're publishing this as part of the core web API. So what happens is if I want to send or read a message, I'm going to basically make a request using message information to the process message task. The process message task is going to start by connecting to the database in the record storage, and it's going to start by actually validating the fact that this user is allowed to send or read messages. Assuming that the user is allowed to send or read messages, then we're going to have a look and see whether or not the request is either an inbound, either we're reading a message, or it's outbound, i.e. we're trying to send a message. So we're going to have a look at the message queue information to see whether it's an inbound queue or an outbound queue. So here, if it's an inbound queue, then we're going to attempt to read a message. Otherwise, it's an outbound request, in which case we're going to send a message. Okay, so let's pull this apart in more detail. Let's go and have a look at what read message is doing. So what read message is doing is very simply going to the data at rest record storage, and it's going to call a stored procedure called GI read message. And it's going to take the information that it was given, and it's going to go to the named message queue and read from the named message queue the next message that's available in that queue. If no message is available, it will just return an empty message GUID and empty data. Otherwise, it returns the GUID of the message in the queue and then pulls out whatever information is there, a sender, a recipient, and subject. So this is an example of where the application, either the user experience or some internal REST logic, is reading the next available message from a named queue within my data at rest record storage. So this record storage is guaranteed to always be there, and it may or may not have a message. So the alternative pathway is that we're going to go down this send message approach. So if I go to send message, you can see that we're calling the reciprocal function GI send message, and all it's going to do is bundle up the message information and actually then write that message information into my queue and return, because hopefully it will work. And if it doesn't work, then obviously we're going to get an exception coming out. But essentially this again is my data agnostic service, my user experience or some REST logic is saying I need to send a message. I'm going to put that message information into my internal message table, and then at some point in the future that table will be read and the message will be processed. So this is a REST interface that is essentially being called in real time by my user experience or by my other functionality. It must be able to establish a connection to my DAS record storage in the same way that anything else for UX or workflow within the DAS solution must be able to work. So assuming that the UX and the workflow works, then the database must be available. So it must be okay for me to put a message into this internal queue or read a message from this internal queue. So that's the population of the internal buffer. Very, very simple, very, very simplistic. It's single record inserts or updates. So let's look at the reciprocal side of this. How does the information get out of that internal table, flow through a generic Windows service, and then end up in an external target? So let's have a look at our processing service. So this is a generic web service that we publish as part of Trellis Spark that you can download from greatideas.com. And essentially what this is going to do is this is going to service one of those internal message queues and push the information out into a third-party buffering mechanism, like, for example, Azure Service Bus or an SMTP POP3 processing. So let's have a look at how this is going to work. So essentially what's happening here is that within our worker process, we're going to be calling an asynchronous task called process. And what this process task is going to do is it's going to connect to the data at rest record storage. It's going to connect to a service account so that it has access to the queues and the definitions of message queues within a particular environment. And then once we've actually connected, we're going to pull down the service definition. So we configure this generic service in Data, and there's whole videos on how all of this is working, so I'm not going to go into that in a ton of details. But what we're looking for here is this line here, where once the service has started up and it's done its connection and it's set up all of its authentication, it's then going to process message queues. So let's have a look at how it's processing the message queues. So here it's executing through the information that it got as part of configuration of the service, and it's looking for a bunch of message queues. And once it's found a message queue, then it's going to go through and process each of the message queues that have been configured that will be consumed by this particular service. And essentially what it's going to do there is it's going to call this function called process messages, and this will be either processing the inbound or outbound messages from the internal message queue buffer to the external buffering mechanism. So let's go and have a look at how this is working. So what process messages is doing is taking the information about the message queue it's trying to process. So it might be the message queue for outbound POP3 email as an example. So it will look at the message information in the queue XML and say, well, what sort of message queue am I trying to process here? And then it will go through all of the different message queues that have been set up as different messages. It will go through all of the different types of message queue that we have set up at the moment. So in this particular case, we have Azure storage queues, Azure service bus topics, event hubs, email POP3, and so on. So in this particular case, we're going to have an example that's going to be a POP3 email example. So essentially what we want to do there is we want to extract from the queue element all of the information that tells us how to actually connect to this message queue. So the queue XML, if we look at the underlying data, it will tell us how this POP3 server has been set up. And then once we've got that information, then what we're going to do is we're going to instantiate an example of a POP3 email class, which will then enable us to go through and read all of the emails that we need to process. So essentially this process here is going through, it's looking at what sort of queue have I got. In this case, it's an email POP3. Great, let's instantiate a POP3 email object, and now we're going to go and process it. So if we scroll down through the rest of the case statement, we can then see, okay, great, I got my information around what sort of queue it is. I've configured an underlying message queue technology, in this case a POP3 client, and now I want to actually go through and work through my message queue, and then in this case I'm going to read a bunch of messages. So essentially what I'm going to do here is look, is this an inbound or an outbound? Well, in this case we know it's an inbound, so we can skip through all of this stuff. So I'm going to go to my inbound processing, and now what I want to do is work through all of the messages that are currently available, and I want to look at my POP3 client. I want to read all of the messages available for my POP3 client, and I want to send them to my internal message buffer, which is the dim messages table. So essentially what I'm doing here in this code is I have connected to my POP3 client. I am now in a point where I want to go through and read all of the messages. So I'm going to use my messaging client to read all of the available messages and put them in my dim messages table. Now, if we look at how this POP3 email client has been implemented, what you'll see is that it is inheriting from messaging base. So messaging base essentially is the underlying interface class that we're using to enable us to use the same interface. So the idea here is the read and the send method. We're using that same interface across all of our queuing technologies. So whether we're talking about an Azure Service Bus or SMTP or so on, every one of our implementations will implement the same messaging base interface. So here, our messaging object has been set up to our POP3 client that we set up here. So here, if you remember, is our email POP3 queue. We're defining messaging to be an implementation of this, and this is using inheritance of our messaging base class, so that by the time I get down here to the point where I'm actually processing an inbound queue, I have got an object in the messaging variable where I am implementing the base class. So I have send and read, and all of the information that is needed has already been initialized in that object based on the queue definition that I processed earlier. So at this point, all I have to do is repeatedly call read until I've got no more messages in that message queue, in that external POP3 message queue. And then for every message I've read out of that external message queue, I'm going to put that message into my dim messages internal table in my data at rest storage. Now, if I was doing outbound processing, it's the same basic idea, right? I'm still going to go through, understand what the queue is, figure out what technology I'm going to be using. So let's say it's an SMTP message queue that I'm going to be sending information out from. So in this particular case, I want to be reading messages from my message queue. And then while there are messages in the messages table, I'm going to want to write them to the external messaging queue. So this is slightly different in the sense that what I'm going to want to do here is that I'm going to want to take the message from my internal dim messages table. So I make the initial read up here. Assuming that I got something to read, I'm going to go around this loop. Within the loop, I'm going to make sure that I can then send the message to that external service. So in this case, say an SMTP POP3 message queue. After the send has been completed, I'm going to want to see whether or not the send was successful or failed. So here, what I'm going to do is I'm going to indicate the success or failure of processing that message by moving it out of the dim messages queue into either a message failure or a message history. So I've got some sort of record of the fact that I sent an outbound message and whether it succeeded or failed, and if it failed, why did it fail? So essentially, this is basically maintaining an audit trail of outbound messages. And then assuming that my process completed successfully and my message was sent, failed, and logged, then I'm going to attempt to read the next messages from my dim messages table and then go back around the loop again. Okay, so you've seen, in essence, the way that we decouple information systems within Great Ideas. We have basically a two-stage decoupling process where the user experience or the REST API automation logic is writing to its internal dim messages table, and that's like one part of the transmission communication mechanism. And then we have a completely separate process where we use a generic Windows service that's basically pre-configured with a set of message queues that it's responsible for, and then that generic service reads through all of the messages available if it's an outbound transmission and sends it onto its third-party messaging channel and makes a note in the history whether it was successful or failed, or if it's an inbound communication, it will attempt to read the external message source and then put the message into our dim messages table. Obviously, on the inbound communication, if it fails, we're going to log the fact that we were unable to establish a connection or read a message from the incoming source. So that covers a lot of what we want to do in terms of communicating data between external systems, but there's an alternative, right? I mean, we might not be able to decouple, and sometimes we are going to want to look at a tightly coupled transfer of information, and this is typically achieved using some form of real-time API call. What we see when we're looking at these real-time API calls is they're typically a smaller data scope. So for example, if I am transmitting an ETL batch file, I might have thousands of records that I want to update all at once. When I'm doing something with a real-time REST API, it tends to be typically like one record I'm trying to process. I'm trying to do something as part of a user experience or a workflow where I have got a record that is currently my focus, my context, and I'm trying to execute some sort of operation on that particular record. So the advantages of this tightly coupled real-time API is, by definition, it's real-time or near real-time. Essentially, what we're looking to try and do here is to execute some sort of external command functionality, which may actually be part of workflow, or it may be transferring data to or from some sort of third-party solution, and we want to happen now. So from that perspective, we're doing this now. The user or the workflow that's triggering this is actively engaged in the transfer process and is waiting for a response. So in the context of a user experience, this can be useful because it means that the user is able to immediately respond if there was a failure. So maybe they retry it, maybe they change some of the data fields and retry it. But essentially what's happening is because I'm doing this real-time interaction, the user is blocked from proceeding until they have responded to the call that was made against the real-time REST API. And this is obviously a good thing in many respects, because the user is already focused on the record. They know whether it succeeded or failed. If it failed, they can retry it or cancel it or do whatever they know. But they don't need to be told a day later that the requests that they submitted the previous day have succeeded or failed. They're in the flow, and they can respond immediately to an error that's coming back. And this clearly, in many respects, is a good thing. But there are downsides to this approach, right? The first one is an increased latency. The user, by definition, is waiting for a response. So if that service that they're calling is slow to respond or is down, the user might be waiting for a minute or two for that service to respond. And most users don't like waiting more than a second or two for an external request to complete. So that can be very frustrating for users, even though the fact that the response fails after sort of like a minute may trigger them to do something else. So one thing that we really need to be cognizant of when we design these systems from a user experience point of view is what will the user tolerate, and is it worth the user waiting for the API to complete and succeed or complete and fail before they go on to their next task. So obviously, once we've got into this point where we have now tightly coupled our user experience or our workflow to this external third party, if that external third party REST API is not available, So let's say we're trying to call some sort of external REST API against a customer to tell them about order information to confirm an order, and their REST API is down. That means that the user's blocked. They can't complete the activity. The workflow is going to fail. I'm going to need to put some retrial logic into my workflow to deal with the fact that this particular customer REST API had failed. And that can get very complex very quickly. So what this then leads to is essentially a fragility in the solution, in the workflow, both from the fact that what happens when that target is not available, it's down, or maybe it's running so slowly that it's timing out. Okay, so all of these scenarios cause different issues as far as the caller is concerned. So we've got logic now that's spanning two systems, A and B, and essentially this makes the solution as a whole less resilient, right? Because we now have a dependency of both systems on that particular interface contract. If that interface isn't there, or if the contract changes, so let's say, for example, I introduce a new version of my recipient API, so A is calling B, and B's contract now changes, it's got an extra parameter, or it's lost a parameter, or the name of a parameter has changed. I now have to go back and rebuild and retest component A to take into account the fact that the component B interface changed. And now what happens when I've got two versions of component B running? So anything that we're doing where we have a tightly bound interface, where we're calling a REST API that's expecting a very specific set of parameters, named parameters, set of error conditions, worrying about whether or not the service is up, whether the service is responding within a particular timeout, all of that basically gives us more fragility in the system, and that's not good. Related to this fragility is that now when something goes wrong, we have an issue where we need to be dealing with a compensating transaction across both systems. So we can't assume that we have an ACID transaction within our data at rest system of record when we're making these sorts of tightly coupled calls across different information systems. So if A calls B and B fails for some reason, then whatever the error in B needs to recover the state of B to an appropriate place, and A needs to recover to the equivalent state as well. So what we've now got again is with a compensating transaction that needs to happen in A and B also needs to be synchronized across both systems. So the more we build these real-time, tightly coupled interfaces using an interface service contract, the harder it is to maintain our systems and integrations into the future. So you can absolutely do it, and there are great times and places for doing it, but you need to make sure that where possible, you have encapsulated that. So let's look at an example of calling a REST API within the Trellis Spark solution. And we're going to pick a really simple mashup that we did with Google Maps. Okay, so we have a whole bunch of detailed videos where we're going through the data presentation layer in extensive detail. But here we just want to call your attention to an example of calling a REST API out of our code. So within our user experience, we have a user control called GI address, which is responsible for displaying an address. And one of the things that we want to do within that address component is go and search for an address in Google to actually make sure that we can pull things like city, town, country, region, postal code, etc. as part of a search, an obvious simple function that needs to use a real-time REST API, right? It is worth waiting for the Google Maps API to give us a list of matching addresses so that the user can pick an address out of here, right? So this is exactly one of the cases where it makes common sense and it is obvious that the user would want to wait for the results of the REST API call to do the next step in their process. So in this particular case, a practice that we want to do is encapsulate the REST API. So at some point in the future, if I want to change the interface, if I want to call a different address provider, that I can do that without having to rewrite any of the rest of my application. So the first rule is if you are going to make a call to a REST API, then encapsulate that within a component so that the actual implementation of that is hidden as far as possible, and it makes it as easy as possible to change that component going forward into the future. So in this particular case, this UX component has got a whole bunch of user experience defined, and then a whole bunch of internal variables where we're actually getting the street name and so on. And then we're initializing our component, and we are going to go through a process here where we are going to invoke our autocomplete. So one of the things that we want to be able to do if we're going to include an external REST API call is we're going to want to make sure that we encapsulate that call within a component or within a piece of code so it's isolated and written once. And the actual REST API call and the processing of that REST API is hidden within the implementation of that particular component. So one of the things that we built in our Great Ideas Trellis Spark solution is an address component. So obviously one of the things that a user would want to do within the address component is start typing in an address and then see a list of matching Google addresses and then be able to pick an address. And this is a classic case of where the user would expect to interact with that list in real time. They will wait for that list to populate so they can pick an item from the list and then move on from there. So here in our code, we've got our generic GI address raiser component. All of this code here in the WASM SA build is available as source code for you to download as part of the Trellis Spark example in greatideas.com. And essentially what we're doing here is we're interacting with the JavaScript runtime to set up an event handler so that when the user is working through the user experience and they come to the address, when they start typing in an address, this is going to initiate an event handler in JavaScript that will then work through a REST API call. It will talk to Google, it will make the REST API request, and then it will start processing the request. So in this particular case, I say we're going to do the detailed deep dive when we look at the user experience, but for this presentation, all you need to know is that as we go through the initialization, we're going to basically set an event handler in JavaScript. And then when that event handler is called from JavaScript, there's a postback that comes back into our Blazor component, and we can take the object that we got from that, and we can then work through the selected item to populate the components of our street address. But the whole process, the encapsulation of this particular REST API call is contained within this GI address component. So if I use an address on like 50 different pages within my application, I've only got one place where that REST API call is being defined and called. And if I need to change that REST API call because Google changes its parameter set or changes the way it connects, or I decide I'm going to use Bing instead of Google, then I've just got one place in my code where I need to come in and make that particular change. So as ever, one of the last things we do in each of our enterprise architecture courses is we look at the impact of this architecture on sustainability of the solutions as a whole. So one of the first things that we should take away from this data flows is that the ability to decouple and buffer communications makes it easier for us to change components. And the double buffering mechanism that we implement within Great Ideas and Trellis Spark is going to really help us to create a complete set of generic message passing components. Because from the perspective of the user experience or any of our automation, all they have to worry about is talking to our internal dim messages table. So we have one simple mechanism for any of our UX or workflow components to say, put a message in the message queue or read the next message available from the message queue. It's simple. It always works the same way. They're always executing the same basic API function call. And then we've got our WS generic service that we looked at, where all we have to do now is take whatever information within that internal message queue buffer and then write it out to whatever the target storage mechanism is. So these external storage mechanisms, whether they're POP3 email clients, whether SMTP, whether it's an Azure storage bus, whether it's a set of shared files, have a very simple common interface. So instead of having to worry about every piece of code in our user experience that needs to send a message, having some appropriate code to write directly to the external messaging mechanism, we don't have that. We have a hop where that code writes to the internal message buffer, and then a second hop where the internal message buffer is then sent to the external messaging provider. And that dual hop mechanism means that we can get away with providing relatively few implementations of the write to an external communications mechanism and a single method to write to our internal buffering. So this really reduces the amount of messaging code that we need to write as generic solutions, and it significantly reduces the amount of message transport code that we write in the solution as a whole. So being able to reuse and build these generic components is really cool, and that's going to reduce the cost of building and maintaining these solutions into the future. And then obviously as the messaging technologies change for the external messaging providers, so let's say for example the Azure service bus interface completely changes and we need to rewrite that communications mechanism, then that's great. I don't have to rewrite any of my UX or any of my workflow components. All I need to do is rewrite the buffering generic service that takes messages out of my internal message queue and puts them on a service bus, or vice versa. Okay, so this makes my solution as a whole a lot more sustainable when we're dealing with third-party changes. The other really cool thing about the data agnostic service architecture is its reach. So I might start off with something that's just doing some HR, and then I incorporate something with doing some CRM, and then I build in some fulfillment. And as I move towards more of a data agnostic service implementation across my solution as a whole, more and more of the functionality comes within scope of the DAS architecture itself. And this significantly reduces the need to move data internally, because all of my individual services, whether they're HR or CRM or ERP, are all accessing the same fundamental data store. So as long as the latest version of the entity is in that data store, all of the services can access that as first order citizens, which means I don't need to move it between different applications anymore. So adopting a DAS approach helps me by minimizing the amount of communications I have to write. It also helps me minimize the amount of communications I actually have to do. And what this does is essentially our data agnostic service approach effectively gives us a jump start in building an effective low-cost entity synchronization layer. So if you look at the overall discussion around data agnostic services in enterprise architecture, one of the approaches that we have from an architectural perspective of integrating data across multiple applications is building what we describe as an entity synchronization layer. So very briefly, this means that instead of having, say, customer information scattered across several different applications, it means that I want to bring the customer information into my data agnostic services as a single system of record for customer data. And then anything that wants to update customer information writes a message into my DAS architecture, and then the DAS is then responsible for maintaining the latest version of a particular customer and then causing outbound communications to all of the other applications to make sure that that customer record is now synchronized. So this whole data agnostic service approach gives us a really cost efficient and effective way of building an entity synchronization layer within a large size organization. As ever, and as we've already touched on, as our data storage or transport technology changes, then it's very easy to update things. So we already gave you the example of what happens if Microsoft changes their interface to a service bus. Well, great, I've just got one class, that's the Azure Service Bus interface implementation that needs to change. And once I've implemented that new change, then all of my rest of my code basically can take advantage of that without even knowing that something changed. So again, from a sustainability perspective, one thing you want to minimize is your dependencies on external third-party systems. So having this mechanism where we have this second layer buffering certainly allows us to make sure that we have decoupled the interface as far as we can. The other thing that's really cool about this process is that when you look at it from an infrastructure perspective, because we basically put the DIM messages table into our data agnostic storage, we don't need any additional infrastructure for that, right? It's just part of the underlying storage architecture. And then our communications to and from the third-party communications is then a minimal implementation of a generic service. So what this typically means is that we're implementing a lot less storage and transfer information in our data layer. And essentially, if we're implementing less services, less servers in that layer, then obviously you've got less infrastructure to maintain going forward. So, from that perspective, we're looking at sustainability. It's also green technology in some respect, in the sense that by implementing an efficient, high-performance solution on a smaller infrastructure footprint, then obviously we're cutting down our carbon emissions as well in some way.
To learn more about Great Ideas products and solutions, visit greatideas.com. That's Great Ideas with a Z.com. Thanks.